Okay, so I'm not there today to talk to you about Newton's second law of motion, but for going through the little bit of notes and examples that we need to do today, you're going to need your forces note packet opened up to this page right here, and then also a blank piece of notebook paper for writing down some Newton's second law calculation examples that we're going to do here in just a moment. So Newton's first law of motion tells us that an object at rest will stay at rest and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. So if there is an unbalanced force acting on an object, it will cause that object to accelerate. Remember, acceleration means rate of change of an object's velocity. So when there's an unbalanced force acting on something, the object will either speed up, slow down, or change direction. And as we've talked about, really, we could boil it down to simply saying that we have a change in motion. Again, speed up, slow down, or change direction. By changing an object's motion, we change its velocity, causing it to accelerate. And so Newton's second law is really the mathematical model that outlines the relationship between the object, which has mass, the unbalanced forces acting on the object, and then how much its motion will change. So Newton's second law, again, says as the mass of an object increases, it will take an increasing amount of force in order to cause it to accelerate. And if we put that in a mathematical relationship, we would write it like this right here. Acceleration equals force over mass. Now on your note packet, I accidentally put mass over force, so make sure you correct it like I have up here on the board. So that is the mathematical model that relates, again, the force pushing on the object to how much its motion changes. Okay, if we look at just that version of Newton's second law, if we had, say, a really big force acting on a little tiny mass, big force, small mass, that should net us a really big acceleration. Now, what if the opposite was true? What if we have a little tiny force acting on a really big mass? Well, we've got a really big, heavy object, lots of mass, lots of inertia. If we don't apply much force to it, that's going to give us a little tiny acceleration. So, big force, small mass, big acceleration, small force, big mass, small acceleration. As we're getting into our Great Balloon Race Challenge here next week or so, think about Newton's second law and what it's telling us. Which of those two scenarios do you want in your balloon racer? Big force applied to a small mass or a small force applied to a big mass? What's going to give you the best chance to win that competition? Now, because this is a mathematical model, acceleration equals force over mass, we can manipulate that mathematical model to solve for one of the other variables. So for instance, right next to our mathematical model here, I have or model number 2. Force equals mass times acceleration. Oftentimes this is the classic mathematical model for Newton's second law, but really the first variant really focuses in on what leads to the change in motion. Acceleration equals force over mass. But we can rearrange it and solve for force. Or, as our third mathematical model, third variant of that mathematical model shows us, if we wanted to know the mass of the object, how much inertia the object has, we could also take the force divided by the acceleration and get the mass from that. So this is where we're going to do a couple of example calculations. We're going to do one example calculation for each of these three variants of Newton's second law. Now there's not really room in your note packet to do this, which is why I suggested an extra sheet of paper, but here we go. So, examples of Newton's second law calculations. Example 1. Our three variables that we need to calculate Newton's second law is force, mass, and acceleration. In this first example, we have the force, 150 newtons, capital N stands for newtons. Mass equals 90 kilograms, kg is kilograms. And then we're going to be solving for the acceleration. Acceleration has units of meters per second every second. Just like when we went through our motion unit, solving for acceleration in that unit. So I'm looking to solve for the acceleration, so I want to use that first version of our calculation. Acceleration equals force divided by mass. With that, I can plug in my 150 newtons. For the force, I'm going to divide that by the mass, which is 90 kilograms. And so if I do my division here, my acceleration is going to work out to be 1.67 meters per second over 1 second. So that's telling me in this instance that that unbalanced force, 150 newtons, applied to an object with 90 kilograms worth of mass, it will either be speeding up or slowing down at a rate of 1.67 meters per second every second. Now for our second example, we want to solve for the mass. And so if we're solving for the mass, we're going to use that third variant of the equation. It's been rearranged. Mass equals force divided by acceleration. And so in this instance, we have a force, which is 250 newtons, and we have an acceleration, which is 1.09 meters per second every second. So 250 newtons over 1.09 meters per second every second. And so again, we're going to divide. And if we divide that out, we end up with a mass of 229 kilograms. Which, if we just compare these first two examples, between example 1 and example 2, in example 1, we had a smaller force than what we have in example 2. We had a larger acceleration in example 1 than we did in example 2, which those things lead me to the conclusion that the object in example 2 must have had a greater mass. We have a bigger force but smaller acceleration. That can only be because the mass of the object for example 2 must be larger than the mass of the object in example 1. Inertia. More mass, greater resistance to changing its motion, smaller acceleration. And then we have our third and final example here. For the third example, we're looking for the force, so we're going to use that second variant where we've rearranged it for force equals mass times acceleration. So we're solving for the force. We're going to put in our mass, which is 250 kilograms. And then we're going to multiply that by the acceleration, which is 0.87 meters per second every second. And so to get the force, we're going to multiply. And so we multiply 250 times 0.87. That gives us 217.5 newtons for the amount of force. Okay, so that's all we had to talk about for today. Again, Newton's second law is quantifying. It's giving us the ability to calculate the amount of unbalanced force, the amount of mass or inertia, and how much the motion is changing or the acceleration. So at this point, you should get Forces Worksheet 2. You have a couple of questions on there to answer, and then 3 calculation problems. Make sure you read the directions for those calculation problems correctly and completely so that you have everything you need for presenting your results in class tomorrow.